So what I'd like you guys to start off with today is looking at this first situation. I would like you to read the situation that's there, and then, if you can, answer these two questions. I expect that some of you should be able to, especially if you're in my class last year. You should have no difficulty doing this. On the other hand, I will expect everybody to be able to draw for me a velocity and a position graph with the information that's presented. So that's what I want from you. I'll give you a couple of minutes to try and do that. Velocity graph, position graph, and if you can, answer the two questions. So I intend to volunteer you guys to speak for me. So I would hurry, but maybe confer with the people around you. I'd love to give you more time, but this should be easy. We've been doing this for the last couple of days. All the information you need is there. I should have pretty straightforward cases of you guys having this one drawn correctly. So, Owen, how do I do this?
For the velocity graph, draw a straight line going up through the x-axis.
Up through the x-axis, the horizontal axis? Like starting from the horizontal axis?
Starting below the horizontal axis. Yeah, something like that.
How many of you agree with this? Nobody's backing you up, buddy. Sorry. That's all right. I do expect a lot, but the velocity goes from 20 to 50, correct? So I think I need to have a graph that's going to accommodate up to a velocity of 50 meters per second. So I'm going to go 10, 20, 30, 40, 50. I'm going to put my units here. Every time you're asked to make a graph, one of the things you should notice is that you earn points for what you do on your graph. There are points to be earned even if your graph is wrong. For example, ensuring that the units and labels are placed on both the vertical and horizontal axis, and that you have appropriate labels, are using the majority of the graph provided and are giving relevant information to the graph. For example, I know that the whole thing takes place over a span of 5 seconds. That's what it says. My starting velocity was 20 meters per second, and my ending velocity was, let me get this up here, 50 meters per second. We are dealing with uniform accelerated motion. So as I said yesterday, while we're dealing with uniform accelerated motion, I would expect this to have a linear relationship. So a straight edge used to draw in a straight line that connects the 20 meters per second to the 50 meters per second is what I would have expected here. Any question about this? There should be some, because not everybody had this. But I am expecting this. But I'm expecting more, because I also asked you to draft a real quick position graph as well, a sketch. And I was not asked the question I would have expected. There's no information regarding position anywhere in the problem. When you're not given a starting position, either ask what is the starting position of the object, or you might have to make an assumption. Now, I was in the room, so I could have been asked this, but nobody did. But I'm going to go ahead and start the object from the origin, which is what you should do if you are not given the position to begin. But I am going to label this position. It's going to be in meters because meters per second is the unit that was used for velocity, so I would expect my position to be in meters. And this is still time, and it's still in seconds, and I know it's going to end at 5 seconds. Now, this part should be pretty easy. We're starting at a position of 0. But when I look here, every one of these velocities is positive, correct? That means that the object always had a positive velocity, was always traveling away from the origin, which means I'm going to put a dot somewhere over there in the positive direction. I don't know where this is, but I know it's got to be away from the origin in a positive direction. Now, I have to connect these two dots, and the way I do so is by looking at the slopes that probably exist at these two places. I know that the slope of the position versus time graph is velocity, so the first slope is 20. I don't have a scale for that here, but I know the final slope has to be 50. So I know the slope has to increase over the course of the object's motion from here to here. So when drawing in my curve, I want to make sure that I draw a curve that shows a clear increase in the slope as I go from my starting position to my final position, but not starting with a slope of 0. All right? So there's going to be a couple of points for your axes, a couple of points for proper use of putting your starting and final position, and a proper display of the curve that would connect those 2 points together. That's how you will earn points. Not done yet. You were asked to find the acceleration and the displacement. Anybody find the acceleration? What'd you get?
6 meters per second squared.
It is 6 meters per second, or 6 meters per second squared. Yeah? Slope. I go from 20 to 50. That's a change of 30 meters per second in 5 seconds. 30 divided by 5 is 6. However, I would like to offer you an alternative. This is the model we developed yesterday, which is the functional relationship between the variables. It's based on the fact that our velocity versus time graph is a linear function. Do you remember this? We got this from y equals mx plus b, but we interpreted what each of these values means, and we gave it a symbol consistent with the material we're studying. We were told that the object had an initial velocity of 20 meters per second, and that it traveled for 5 seconds and finished with a velocity of 50 meters per second. Seems to me like you didn't have to find a slope or draw a graph if you didn't want to. The model has to work for all conditions of the model, and this is a condition of the model. So because I knew the final velocity and the initial velocity and the length of that time interval that connected them, I could solve for the acceleration this way, and it would work just as good. Notice you'll still get 6. Questions? All right. Let me get rid of this for a minute because we have some other work to do. You were asked to find the displacement, and here's where you might have been at a loss, and that's okay. Some people should have been able to do it because they're in AP Physics 1 last year, and some of you who may have had honors physics could have been able to do it as well. Let's assume that you couldn't. I told you guys that one of the things you should always do is check for the meaning of the slope and the area for any graph. To do so, you take the 2 units and you find the quotient, because that tells you the meaning of the slope, and you find the product, which will tell you the meaning of the area. We already know that the slope of this line is the acceleration, but the area of the graph may also have meaning. The units would be meters per second times second, and what unit is that? Meters. We have a variety of things that we measure in meters. But if we look at our vocabulary for the unit, it's 3 things measured in meters: position, distance, and displacement. I think the area of this graph is one of those. Position doesn't make any sense. Distance or displacement does. So I am here to tell you that the area under a velocity versus time graph is displacement. That's 3 different things you should know now. I hate to sum up because it makes me feel like I'm repeating myself, but you guys don't tend to write things down. For a velocity versus time graph, the slope is the acceleration. For a velocity versus time graph, the area is displacement. And for a position versus time graph, the slope is the velocity. I know you're going to make me repeat that, but write fast. For a velocity versus time graph, the slope is the acceleration. For a velocity versus time graph, the area is the displacement. And for a position versus time graph, the slope is the velocity. We got it? Comfortable to move on? Good. So let's find the area. First thing I would consider is that we need to figure out what shape we've got going on here. What shape is that? Do we have a clue? How about all those A's you guys got from geometry? I should be able to at least get a word out of you out of what this is. I got 2 parallel sides and 2 sides that are not parallel. So it's a trapezoid, that's right. Quadrilateral would have been okay, but that's just a bigger word. Trapezoid is what this one is. And because you all, almost all, got A's in geometry, you should be able to tell me how to find the area of a trapezoid. Because you are successful and you earned that A and know things. I have two people who think they know it. Let's see, what do you know in the back?
Isn't it the two parallel?
Are you asking or are you telling me?
I'm not entirely sure. I forget. It's been a while.
All right, well, I don't want to be asked, I want to be told.
1/2 height times the base 1 plus base 2.
That is the area of a trapezoid. 1/2 sum of the bases times the height. Because it's the average height of the bases, or average size of the bases times the height. Now, I am concerned about what you don't remember from your geometry class, but the bases are the parallel sides, and the height is the perpendicular distance between the bases. I'm saying it because I'm afraid you don't know. That makes this base 1 and this base 2, and this being the perpendicular distance, this is the height. So the area will be 1/2 20 plus 50 times 5. So can you tell me what the displacement is? Or do you need to punch buttons? Because that'll make me sad. I mean, 50 plus 20 is 70. 70 times 5 is 350. And half of 350 is 175. Good, good. If the old man can do it, then the youngins can do it. That means we know this point, don't we? It was 175 all along, and you could have labeled it on the graph because we now know it. You doing all right? Area is the physical area bounded by the curve and the horizontal axis. I'm not saying this to confuse you or to repeat myself. I'm saying it because it's going to come up here in some of our examples where area might be a little bit more challenging to figure out. So I'm saying it very clearly. When you're asked to find the area of a graph, it's the area bounded by the curve and the horizontal axis. I want to take a moment to bring together something that we just did. First, we have a model already that relates the motion variables based on the idea that a constant acceleration creates a linear function. We now have a new relationship brought to us by the idea that any function is going to create a triangular or rectangle or a generic trapezoid. We could use the area function to produce a new relationship that could help us determine the relationship between variables for motion. If area is defined as displacement, and this is the symbol we use for displacement from last week, then the first base was the initial velocity, the second base was the final velocity, and the whole thing was the time. And oh, I wrote T here. It's supposed to be an H. Sorry, thanks for not correcting me. But the height was the time. These are still vector quantities, but we're multiplying two vectors by a scalar. That leaves us with a vector, which is why delta x is still a vector. I'm giving this to you because I want you to do, you got it written down there? So I want you to do this one. Repeat our work. Try it again. This time I expect perfection. Velocity graph, position graph, and the answers to this question. For the most part, I saw lots of good stuff here, so I'm not going to belabor the point too much or spend a lot of time calling you guys out. I saw on many papers that you started this at 6 meters per second and drew a nice straight line ending at 3 seconds. Good job. That's what this should look like. I saw a few missteps with the position graph that's going to come at a cost to your grade. So, first, part of the reason we're practicing is because when you're going to do this for a grade, say tomorrow, I want you to have practiced. If you're not writing out the labels, using a ruler to make your line straight now, are you going to do it tomorrow? You'll forget, promise. I've seen it before. Nobody asked where the object started, so I assume we started at the origin. And just like before, every single one of my velocities was positive. Doesn't matter that it was slowing down, every single velocity was positive, which means after some amount of time, the object was away from the origin. At time equals 0, the slope was 6. I don't know what 6 is, but it's positive. And at time equals 3 seconds, the slope was 0. I suspect then that I can connect these with a smooth curve. That's what I would expect to see. A few of you had missteps. I am a little disappointed in the ones I saw that looked like that. A little disappointed. Saw a lot of that 6th period. Acceleration, did you figure it out? Negative 2 meters per second, sure. I mean, if you did the slope here, the rise is negative 6, and the run is 3, negative 6 divided by 3. Or you could have used the model, V equals AT plus V naught. The model would have worked, right? 0 equals A times 3 plus 6. This would yield negative 2 meters per second squared.
I used the model, but how do you use the slope?
The rise here over the run, I go from 6 to 0, that's negative 6, and from 0 to 3, that's positive 3. Displacement would be the area in here. I think that one wasn't too bad either, was it? Again, you can use the model, or the fact that it's a triangle, 1/2 base times height, so what did we get for the displacement? 9. Yeah. If we use the model, 1/2, initial velocity was 6, final velocity is 0, time was 3. It's going to give you 9. So, let's see if you can adapt. All right? We're going to look for your adaptability. All right, let me take back over here because I'm seeing some interesting stuff. Considering the ball in the previous example, it rolls up the ramp at a speed of 6 meters per second. But instead of being caught at the top, it rolls back down until it's traveling 8 meters per second in the opposite direction. So my thoughts are that whatever it did for the first 3 seconds is probably repeated here, right? 1, 2, 3, 4, 1, 2, 3, 4, 6 meters per second, negative 8 meters per second. Opposite direction. Direction is denoted by positivity and negativity. So if 6 meters per second was the positive direction, then when it's traveling in the opposite direction, it has to be traveling 8 meters per second. I will assume it takes still 3 seconds for it to come to rest before it turns around and comes back, but I want to be careful here to try and make this look right. We don't know how long it took for the object to return to where it was. We just know that this point is 3 seconds. We don't know where that point is. But this is what the graph should look like. The thing that I can count on probably is that the slope is the same, right? The ramp was the same angle. I would expect the ball or the cart or whatever to experience the same acceleration if the ramp was the same angle. That's the clue that we were told the acceleration at the start of this problem because we found it in the previous problem. Seems to me I can figure out what that time is by using my model, right? This model. Final velocity was 8 meters per second. Acceleration was negative 2 meters per second squared. times t plus the starting velocity of 6 meters per second. 8 minus 6, negative 14. Negative 14 divided by negative 2, and time equals 7 seconds. Did I do anything weird? Saw some weird graphs out there. But it's still going to be a straight line graph. The object's still experiencing constant acceleration. Velocity graphs for right now will be linear. You can count on it. That won't change until next week. But end of next week it's going to change. Now, more to talk about here because I saw some weirder stuff when you guys are trying to figure out how far the ball went. I tried to say it out loud to you before you launched into it, but area is the space in the graph bounded by the curve and the horizontal axis. So there's an area here, and there's an area here. Those are our two areas. One of these areas we know. This area is 9 meters. We found that out in the first part of the problem. One of these areas we didn't know. We will have to figure it out. What is this area? I don't think it's 16. I think it's negative 16. Sure. Areas on the positive side of the graph produce positive areas. Areas on the negative side of the graph produce negative areas. Now, negative areas aren't like they're, area in the void or something like that. A positive area represents positive displacement. A negative area represents negative displacement. And if you don't know where the 16 came from, it's a triangle. This is how long?
4.
It is 4 seconds because this point is the 7-second mark. This is negative 8 meters per second. 1/2 base times height. Negative 16 meters. Okay so far? Now, answering the question might involve some consideration of what's happening. You roll the ball up the ramp at 6 meters per second. How far does the ball travel before it comes to rest? 9 meters. The ball travels 9 meters before coming to rest. Then the ball turns around and comes back. How far does the ball roll back? 16 meters. In this direction, 9 meters in that direction, before not coming to rest, but having a velocity down the ramp of 8 meters per second. This is the order of events, what happened to the ball, correct? How far did the ball go? See, we have some concern about this. This speaks to the difference in the word distance and displacement. Displacement has been defined for you already as the absolute change in position. It's defined last week. Distance is how far something goes. The ball traveled 25 meters. 9 meters up the ramp, 16 meters down the ramp. So the total distance traveled is 25 meters. Distance is a scalar quantity. Now, to determine distance, you need to figure out the partial displacements. You need to figure out the displacements that are positive and the displacements that are negative. And then make them all positive and add them together. If you want, I can say it as a rule that distance is the absolute value and sum of the partial displacements. As the rule goes, it's kind of dumb sounding, but it's the truth. Distance is the absolute value and sum of all the partial displacements. We had two partial displacements. The displacement up the ramp and the displacement down the ramp. However, Do I need to say it again? You guys are still writing. We're good? All right. However, and I want to emphasize this, the total displacement was 7 meters. During the 7-second time interval, the ball is now 7 meters behind where it started. Now, I need to show you something because I need you to be careful. This doesn't look like a trapezoid, but it is. In Euclid's geometry, you can't have occlusions into your area. But in non-Euclid's geometry, you can. This is a trapezoid. It's what would happen to a trapezoid if you took the two bases and flicked it like a car sunshield, you know, right before you fold it up. You guys know what I'm talking about? People look at me like crazy, but you take it and you flip it in half. That's what's happened here. And you have what's called an occlusion in the middle of your area. I know that sounds weird, but it's true. And we can kind of prove it. Delta x equals 1/2 v naught plus v times t. This is our trapezoid formula. So 1/2 v naught was 6, v was -8, time was 7. Right? You see where I got all those things from? 6 minus 8, -2, half of -2, -1, -1 times 7, -7. The displacement formula gives you displacement, does not give you distance. And if you find the displacement over the entire interval, you get the total displacement. Always know what it's providing you. I have more to do today, and the next part's going to be a little bit more challenging, but I think I'll take a moment and sum up, okay? So I'm going to go someplace where I can sum up. At this point, I want you to recognize that we have brought together 4 vectors and 1 scalar for a total of 5 motion variables. Displacement, initial and final velocity, acceleration, and time. By final velocity, we mean the velocity at the end of a time interval, denoted by how much time was allotted for the interval. Acceleration is exactly what it says, but we're dealing with a certain kind of acceleration in this unit. Right now, it's constant acceleration. Using data we derived from actual objects on the track, we figured out that there are relationships between these variables that we can count on as long as the acceleration is constant. This is one of them. And this is another. These are functional relationships between the variables that can help us answer simple questions and make predictions about future events. However, and this is where all of you who have not been paying attention because you're in AP1 last year and you think you know all this need to pay close attention. Only one of these is a motion variable, or motion equation. These may all be motion variables, but only this one is a motion equation. It might not sound like an important detail. It's incredibly important to me. In a week, we'll be deriving motion equations, and motion equations have specific requirements. Last year, I would have referred to all of these as Galileo's motions equations, and I won't in here. I'll just call these Galileo's equations. They work for constant acceleration, but this one is a motion equation. What sets it apart is that equation is based only on initial conditions of the problem and predicts future values. It tells you a future velocity based on the starting conditions. Initial velocity and acceleration. This does not do that. This tells you the displacement, but I must know a future idea. I need to know the future velocity in order to determine the displacement. It's not based on initial conditions, but on future conditions. It's recursive and not a motion equation. However, you guys are smart. It could become a motion equation. It can become one because you know algebra. And I have two relationships that have final velocity in them, but one of them only has initial conditions in it, this one. Through substitution, you should be able to create a new equation here that eliminates final velocity and introduces initial conditions. Which is a lot of words for me to just say, I want you to use substitution to eliminate final velocity between these two equations and create a new one. We only have 5 minutes left, so you have 2 minutes to do that. Do your algebra. You are good algebra students. You got A's. And for those of you who are just looking at the paper, not knowing where to begin, you're taking this and putting it in for velocity here. You can do this. That's called substitution. Hurry. You have 1 minute and 30 seconds left. V, straightforward substitution. I created one equation. Now, collect like terms and expand. I have a V naught and a V naught. I can add them together. And I will get 2 V naught. I can distribute the T. I can distribute the 1/2. At this point, you could argue that you're done. You have done the process that I asked, but I'm going to ask for one further thing so I can make a point. Displacement is x minus x naught. I can solve this for x, the final position, in terms of all initial conditions. This is a motion equation. And if you look carefully, you should see something here that I've been trying to talk about all week. Do you see it? Do you guys see it, please? You understand what I'm trying to show you here? This is why it's not exponential and was always quadratic. It's predicted by the math to be quadratic. Now, this is only true for situations in which the acceleration is a constant. But we've now built 3 things here. And we've built them from data. Delta x equals 1/2 at squared plus v naught times t. I'm adding it to the list. Do you notice something? You may not. So let me draw your attention to it. The first equation has every one of those motion variables in it except for displacement. The second one has every one of those motion variables in it except for acceleration. The last one has every one of those motion variables in it except for final velocity. You understand, through substitution, there's probably 2 more out there, right? There should be one that doesn't have initial velocity in it. So, solve this one for initial velocity and substitute again. And there should be one that doesn't have time in it. Maybe solve this one for t and substitute again. Please bring these to school tomorrow. And at the same time, now that you know these things, yes?
Should we submit the second half or like?
I would like the second page to be submitted for homework, yes. I'd like you to try them out tonight. They should not take you more than a couple of minutes each. I don't care about the velocity graphs, I care about the answers to the questions. Go ahead, these equations just bring to school tomorrow.
What about the first half of our notes? Should we
No,
submit that?
I don't need the first half. We did the first half together. This should be easy. Use them.